We're trying to find what is that optimal combination of materials to then accomplish the customer's objectives. All of this is really just trying to keep their systems up and running to avoid downtime and planned maintenance according to their schedules. Using that information, we can extract the appropriate parameters to pass into the macroscale simulation. As you start to combine simulation with, let's say, some of these machine learning techniques out there, we can take the strength of simulation to kind of evaluate different materials. Then we can use adaptive DOE to combine these materials in different ways to see, okay, we have a new formulation. A big area of research in molecular dynamics is coming up with an accurate way of representing viscosity, or give the agent the ability to go and say, I don't know enough about this, let me go and run a simulation.
All right, Richard, thank you so much for being on the show today.
Hello, Jousef, how's it going?
All good, thanks for asking. Today we'll talk about a very nice and interesting topic, which is about disrupting lubrication with digital simulation. So first of all, a lot of people probably won't know what lubrication is in the first place. Maybe they have some idea, but I think we want to talk a little bit about the theory, about the practical applications, how we take this thing from the real world and put it into a digital simulation pipeline. But before we jump into that, as always, can you give us an introduction to yourself, first of all, and what you're doing at FUCHS?
Sure thing. Yeah, my name is Richard Bellizzi. I've been an engineer at FUCHS for around 10 years now. My background actually was in mechanical engineering. So, I started out developing systems, building systems. That brought me into computational design and systems. So I started doing AI and machine learning. And then we wanted to see how that kind of merged with simulation. So I kind of have a little bit of mechanical engineering, a little bit of AI background. And then, more recently, I've been getting into the simulation space.
Yeah. Talk to us a little bit about the topic of lubrication. Maybe let's start very, very easy. What is lubrication in the first place? I think some or most engineers are familiar with what lubrication is, but why is it such a tricky topic or such a delicate topic to deal with, especially when we talk about testing, but also then putting it into a simulation pipeline?
For sure. Yeah. I mean, lubricants, it might seem like not too complicated, but it's actually at the crux of quite a few different domains. You have chemistry, you have mechanics, you have fluid dynamics. So it actually encompasses quite a bit of engineering capacity that's required to solve these problems. And, formulating these materials, we're taking different combination of materials, combining them, and then having to test them in laboratory environments. And so this can be, kind of a tedious process, time consuming, as we're trying to find what is that optimal combination of materials to then, accomplish the customer's objectives. So, that's really quickly in a nutshell what lubrication is. But I mean, I think, if we had to talk about what lubrication is solving, the main ones are always friction, where, anything that is moving, transferring energy, we want to have a lubricant there to help kind of facilitate that motion.
Yeah, that makes sense. When we talk about kind of the topic of predictive maintenance, where does this fall into place when we talk about lubricants?
Yeah, I mean, so for predictive maintenance, we see a lot of customers, they're not as, like you said, they're not as knowledgeable about lubricants. So, they have bearings in their manufacturing process. They'll have gearing systems, let's say, in turbines. And, they're not, as aware of what's going on with necessarily the lubricant. They understand the full system. So, lubricants, we've seen issues where, they maybe need to refill the lubricant and they put too much in there. That causes issues in the system, causing downtime. So, by providing some predictive insights into how the lubricant is behaving and performing, we can provide recommendations on, do you need to relubricate because, you're running out of lubricant, or did you over lubricate? That's going to cause a bearing failure prematurely. All of this is really just trying to keep their systems up and running to avoid downtime and planned maintenance, according to their schedules.
I see. So how do you actually take these signals from the test bench? I would assume you start first on the test bench and then move it over to the digital pipeline. In both cases, how would you do it in terms of like measuring signals, and how does it look like?
Yeah. So, we working in the applications lab, we've built quite a few different test systems to measure how the lubricant is performing in a customer physical system, right? This could be a gear assembly. This could be, a plunger, that is, has some lubricant in there to dampen it. So, we've looked at different types of sensors like thermal IR cameras, vibration sensing for, monitoring the dampening capabilities. We are researching and looking into different ways to capture some of the chemical properties. And so all of these are kind of clamped around the system to help us kind of monitor what is going on within the system, specifically to the lubricant.
I see. When you then transfer what's happening in the real world and try to mimic it as good as possible into a simulation environment, how would you do it concretely?
Yeah, so I mean, there's kind of multiple stages. So, if when we think about lubricants, we typically will start from the chemistry because, that's driving a lot of the behavior. So we'll look at kind of the, temperature of the environment. We can look at kind of what are the forces, like if it's in a gear, something, how much pressure is the fluid of the lubricant kind of experiencing in those environments. And we can take those parameters and bring them into a molecular dynamics simulation where we can kind of simulate these, stresses on the actual molecules themselves to see, how are they going to behave under this type of environment. This can then yield certain types of macro properties, such as, thermal stability values like thermal conductivity coefficient that can then be transferred into a, macro scale simulation. So trying to take, molecular dynamics to generate parameters that can then be passed into, other simulation software that can then tell us kind of more of long-term behavior. So it's like molecular dynamics gives us a snapshot of what the chemicals are going to experience, but then we can try to generate properties that are then used in kind of more your standard engineering simulations.
Is that what you would call the simulation pipeline? Basically, you take it from the micro level, look at it at the micro level, and then go to the macro level. Is it kind of a coupled simulation to some extent?
Yes. Yeah, molecular dynamics is probabilistic by nature. So typically we are running quite a few of those simulations to get a statistical representation of what the lubricant is going to do. And then, using that information, we can extract the appropriate parameters to pass into the macro scale simulation.
Okay, that makes sense. What simulation tools are you actually using then for the pipeline?
Yeah, so, during the exploration phase, we've leaned a lot onto the open source community. So, we're looking at molecular dynamics software such as LAMPS. It's a large atomic molecular modeling suite. So it allows us to, it's pretty robust in terms of what you can tweak and adjust. And, more recently, there's the rise of machine learning force fields. This is basically the driving solver behind what how those molecules are going to behave in this simulation. So this is really unlocking quite a lot of different opportunities now, across the material science industry, I would say.
Yeah. I'm wondering, maybe if we take a step back later on, we'll talk about again the simulation bit. What physical effects or maybe let's say parameters are customers interested in when choosing for a specific lubricant? Obviously, it might depend on the type of application, etc. But what are customers actually looking for?
Yeah, definitely. To your point, there's numerous applications. Aerospace, automotive, marine, medical. So they definitely have quite a set of different parameters that they will require. But there are some that are overarching across a lot of them. Rheological traits. What is like the dynamic viscosity? How does this, whether it's a non-Newtonian grease or if it's an oil, how does that fluid behavior in the application? Dampening and vibration. A lot of times we do things with motion control to try to regulate vibration in a gear set and things like that. This can be another one. Obviously, temperature stability. We always are getting more and more. We need higher temperatures or lower temperatures. In the aerospace, we have outgassing parameters where we basically don't want the chemicals in the lubricants to be released into the atmosphere. So we have quite a variety, but we can always come down to reducing friction in the wear. And then we tend to add temperature, rheological properties on top of that, or corrosion inhibition, to protect against corrosion. I could keep going on. There's quite a few.
Yeah. When we talk about the lubricant formulation, because there's obviously kind of the secret sauce for the lubricants, I'm wondering, is it only based on experimental testing, or can you also derive some new formulations from the simulation, so from the digital replica, so to speak?
Yeah, this is an area I'm very excited about. As you start to combine simulation with, let's say, some of these machine learning techniques out there, such as adaptive DOE, we can take the strength of simulation to kind of evaluate different materials. Then we can use adaptive DOE to combine these materials in different ways to see, okay, we have a new formulation, and then using simulation again to evaluate the formulation. So we kind of identify, evaluate materials, use adaptive DOE to combine these materials, and then use simulation to evaluate the full formulation as well.
I see. Okay. Yeah, very straight to the point. I like that. When we go back again to the kind of digital simulation pipeline, however you want to define that, what a pipeline looks like, how does the stack look like? We briefly talked about it from the beginning to the end. So how would you describe kind of the pipeline and how does it look like?
Yeah, so we've recently been doing a lot of work in getting our internal data structured and architected. So we have a library of molecules, these 3D structures that we can take into the computer. Typically from there, there's a quantum chemistry calculation that's performed. Basically this is to try to take that chemical structure and, make sure it's representative of what you might see in the real world. So it's kind of optimizing it, making sure it kind of is in the right form factor. From there, there are tools to take that individual structure and generate a system, right? So let's say I want to take that one molecule and go to 100 molecules. And, that is, we use that to kind of basically automate going from single structure, optimize it, bring it into molecular dynamics into a system of 100 of versions of them. From there, molecular dynamics has access to this universal force field, which is AI driven. So now it's much more flexible. In the past, you were kind of pinholed into what was available for those force fields, but now it's very general. So now we can basically take that, pass it into MD with 100 molecules, basically setting temperatures, pressures, everything that's going to drive the environment that the molecules are going to experience, and then we let that run 100 times, 1,000 times. This is where compute constraints tend to come into play, I would say. But then from there, you take those 100 or 1,000 molecular simulations, and then you can calculate some parameters from all of that output data, and then those parameters are easily passed through like an API into a CFD software. Like Dive is a SPH software that we're using. So they have an API which makes it very easy to extract the parameters from MD and then take those parameters and pass them into Dive to start some pre-configured simulation.
Any reason specifically why you've chosen for Dive as a kind of, or at least like the SPH solver? Why an SPH solver, not like a volume of fluid?
So I'm going to give a sneak peek. I mean, this is still very much research, so I want to kind of preface that, but we identified molecular dynamics as kind of like each atom is connected through a bond, so you kind of have these particles in space connected through bonds, right? So when I was looking for a CFD software to kind of bridge the macro scale simulations, I first started with OpenFOAM, again, looking at open source. But there was something very appealing to the particle-based nature of SPH, where, going from a molecular dynamics, atoms as particles, bonds as edges, how that translated into SPH, where you had, the actual fluid particles and then the interactions as edges. And the reason I'm saying particles and edges is my core background is actually really AI machine learning, and there's an area of machine learning AI called graph neural networks. And this is basically representing things as nodes and edges. And so the parallel between MD with nodes and edges and the parallel with SPH and nodes and edges seems like a pretty good fit to basically start to bridge this kind of gap between the systems, as well as potentially, in the future, looking to kind of consolidate a digital twin using this type of approach.
That makes absolute sense. Do you have also MATLAB or Python in that pipeline somewhere integrated?
Yes, I use Python extensively. It's used for like data processing, connecting between the API systems. It actually does a lot of the bulk of the machine learning work that we're using. So Python is used pretty heavily. We are using MATLAB as well. This is, we had started with MATLAB for some of the machine learning work. Python kind of gave us some more flexibility in some cases when we wanted to kind of automate down the stream. And then if I had to mention one other software, we are looking at COMSOL for things like multi-body dynamics in the future. We really want to try to tie this whole end together, from chemical to fluid to kind of what, we talked about vibration sensing earlier, to generating a potential simulated vibration analysis as well.
Yeah, maybe I've asked the question already, Rich, but how do you take the parameters from the molecular dynamics simulation and the ML generated parameters and put them into Dive? Is it pretty straightforward, or would you say there's some specific things that you have to take care of?
So this is where we are actively researching, right? So let's take, we're talking about a CFD software. So viscosity is a big driving factor for how the fluid is going to behave. And I would say an area of research in molecular dynamics is, coming up with an accurate way of representing viscosity, or to calculate viscosity. This is where we think, machine learning can really help bridge the gap. We are positioned, because we've worked in this area. We have a lot of data around, different types of non-Newtonian fluids and Newtonian fluids. So to actively work towards a hybrid system with molecular dynamics and machine learning to augment and make those viscosity predictions. So, right now, just as to build out the pipeline, where we're directly computing the viscosity from these MD simulations, but we need to enhance the accuracy a little bit. And so that's where we're looking at machine learning to help augment that pipeline.
I see. Okay, that makes sense. From a real world testing scenario, how much does simulation support you guys in kind of testing kind of the extreme cases?
Yes. This helps quite a bit. I mean, from my experience, I worked a lot with the chemists in the chemistry lab where we have kind of property tests that evaluate a single point property for that lubricant. I've also worked in our applications. I worked in our applications lab where we would build an engineering system. So like sensors, motors, driving the whole system, running it for weeks on end, and using sensors to gather the data. But this can take like months, weeks. Sometimes that's too long for us when we're trying to go and iterate fast for our customers. So by using simulation, we can test those extreme scenarios, right? We can start to understand the edge cases that our lubricant might start to experience, and that really helps drive us our initial experimental tests towards a solution faster than when we're starting from scratch. I mean, some of our research programs take years, because we're iterating and going through this process. So if we can shorten that development cycle, we can get these products out to our customers faster.
Yeah. For the future development, Rich, how do you imagine, because we mentioned the pipeline, right? The testing part, the simulation part, then AI comes into place or falls into place, and then also the optimization bit. How do you imagine that to happen in the future, like a full end-to-end pipeline? And what can be, compared to the status quo, can be optimized in the future? What would be your wish, your personal wish?
Yeah, I'm a big fan of democratizing these tools. I feel that between the chemists and the engineers, they can all benefit from having this digital playground to experiment and innovate in. So the idea would be, can we set up this UI experience where we have access to AI, we have access to simulation. Some of the complexity is abstracted away, because I get that, like some of the any simulation space you go into, there's a lot of learning capabilities. I went through that when I was trying to learn a little bit about SPH, and so using software like Dive, where they kind of make that a little bit easier to streamline the process of using SPH. That means now we can start to integrate these tools, giving the chemist the ability, rather than have to just think in their head about different options, and then because we're limited in materials, go into lab and make those. Now they can go onto their computer. They have this virtual testing playground where they could, identify materials, test those materials like chemistry properties.
Mm-hmm.
Potentially, once they've gone through that stage, they could say, "Oh, well, I've got some ideas for materials. Let's try out some formulations, generate some formulations, and then those formulations now can be evaluated in Dive in like a macro scale environment." So, I would love to see a future where we have our database of materials, and the chemists are, I'm looking at these combinations, providing some of their own insights, going through that pipeline of exploring the outputs from chemical properties and macro scale properties, and then based on that information going to the lab and then experimenting. So it's like gives them kind of the best of both worlds, where their knowledge and experience plus a place to kind of test all of those ideas out.
Yeah, I see. You mentioned that you started out with OpenFOAM a little bit, try to experiment with it a little bit. So how did Dive CA actually help you find solutions faster? Was there actually some concrete results that you got from using SPH?
Yes. I mean, open source is wicked powerful, but there's always the learning curve of having to learn the new solvers, the software, integrating them, and in environments where maybe you don't have like all of the resources necessary. Something like Dive, where they've made interfacing and running these simulations fairly seamless, to the point where I think the chemists or the engineers would have no problem setting up an environment, running a simulation without necessarily knowing all the underlying SPH principles. Whereas when you start to look at some of these open source ones, you do need to dive in and understand the solvers quite a bit to get the most out of it. So just that aspect, I think we get value right away, right? I mean, we have our SolidWorks models for our application systems. Those can easily be migrated in. Setting up our non-Newtonian fluids, we have a lot of that internal data, so we're able to very quickly kind of map our material properties in. This is like, let's say, without simulation, just going from our lab experimental data into Dive, and then from there, now we can simulate non-Newtonian fluids. Now we can simulate our oils. A good example is an FCG gear system, where we've been able to look at different oils, different greases, looking at the power consumption, thermal stability, and this was all done in a quick, short trial period of time, that really showed how easy it would be to kind of get up and running and get some valuable data out of it.
I would probably assume also in terms of like the pre-screening mechanisms, you would be very quick as compared to your competitors who are also like moving in that space.
Yes. Especially, with the recent upgrades around GPU access, the amount of simulations and the speed of simulations, we can run through quite a few of these scenarios. Within a week, we can explore way more than we would have ever explored in a year. Let's put it that way.
Yeah. What would you say, because we just talked about kind of the competitive space, what do you think some unique insights FUCHS gains from simulating lubrication at different scales? Because we mentioned kind of the different scale levels, so to speak. What do you think advantage you have by doing that? I'm not sure if everybody does it actually in the industry.
Yeah, I think it's still like the simulation. I think is still somewhat new to lubricants. I think there's a lot of research going into this at universities, but in industry, I think the adoption of simulation is still growing. The advantage I think it gives us, looking at the multiple scales is, as our customer applications are getting increasingly more complex, sometimes these chemistry benchtop property tests, they aren't translating one-to-one to what we're seeing in the field, right? This is kind of where the applications lab spawned, where, we wanted to simulate the end customer environment as closely as possible with a physical system. But even that, sometimes that can run for months on end, and that is still too long, right? So the idea of being able to evaluate digitally at multiple scales, again, it's just kind of allowing us to solve more complex problems, right? And we're doing that in a shorter amount of time. The combination, I'm going to continue to emphasize that combination between being able to simulate data and properties, and using adaptive DOE machine learning tools to basically drive which simulations are going to be most valuable, which ones do we care about, to then find those sweet spots for different formulations is really where we're going to start to see it shine. And a lot of this is driven by our internal data, which is continuously getting better. So I think we'll continue to see the value increasing as things start to continue to fall in place.
Yeah. The reason I like this podcast so much is because you talk about literally the practical applications in the industry. And one thing I wanted to ask you is, there's a lot of marketing fluff out there, right? Every simulation window talks about time to market reduction and kind of the typical things people seem to be interested in, or people assume, or the simulation windows think people are interested in. What are the actual benefits of Dive CAE when it comes to kind of time to market reduction? You don't have to talk about concretely right now in terms of numbers, but what are some of the benefits like IT infrastructure, GPU acceleration, etc., that you see as a huge benefit?
Yeah, no, I mean, looking at, running it in the cloud, I like the credit system. So basically allowing any user within the organization to be able to tap into Dive and run simulations. Again, it really supports this democratized simulation where people can kind of go in and experiment. And getting it up and running was very easy, and not having, let's say, all of the IT capabilities to support our own internal HPC system, having that access to the cloud is really powerful to not have to have the stress of managing all of the infrastructure required to support solve solutions like this. So I think overall it has been much easier to get off the ground than when I was looking into the open source solutions. So like looking at months of lead time trying to get everything working till like within a few weeks I was up and running.
How would you say the parallelization aspect helped improve your testing or like the R&D efficiency overall?
Yeah, I mean, being able to run multiple simulations at the same time is super powerful. I have a very personal experience with this because, we only have kind of limited compute internally. So we're always running like sequentially, right? So now being able to run a bunch at the same time, again, it's always coming back down to time efficiency savings, where now we're exploring hundreds of options in parallel rather than looking at one after the other, which, even if it's automated, that's still faster than, going to lab, but looking at 100 in parallel, now we're seeing acceleration like we've not seen before.
Let's talk a little bit about real-world use cases so people can actually grasp kind of not only the theory of the lubrication R&D topic, but also like what can be done in the real world using simulation and testing and combine all of that together.
Yeah, so what we're working on, right? I mean, I think digital twin is a big topic, right? And, when an active area of research for us right now is looking to see, can we create material digital twins? I think a lot of the digital twins that I've seen, looks at, they look at the sensor values just like what we're going to do, but they're focused more at the external system, the gear system itself, the bearing system itself. Can we flip that paradigm and try to understand, okay, how is the environment affecting the lubricant rather than like how is the lubricant affecting the environment, I think, which is kind of what is going on when you're looking at the system rather than the lubricant. And in this way, we can provide more informed decisions. We understand the chemistry, we understand the materials that went into it. So, as it starts to experience different pressures or temperatures, we're monitoring that through the sensors. We can reevaluate through MD simulation to see is our formulation stable still? Is it is there degradation occurring due to pressure, due to temperature? And then with those insights, again, now we can inform our customers. Oh well, your corrosion inhibitor is starting to run out. I think it's a good idea for you to relubricate to avoid any corrosion forming in the near future. I mean, at the end of the day, it's going beyond just anomaly detection, and we want to be able to provide informed decisions around. Okay, here's the cause, and here's your action to resolve that.
Yeah. Do you have like concrete use cases from the automotive or aerospace sector that you can talk about? If you can, of course. Maybe I'm asking too much.
Yeah, I would say this is still fairly early in research. I'd say some of the simpler use cases. Let's say, when we're looking at IoT for lubricants, in the past we looked at metalworking, right, where we're drilling or shaving metal in a manufacturing environment, and sometimes those particles can contaminate the lubricant. So we were monitoring the oil that was relubricating this machining tools and seeing, okay, has that contamination level increased to a certain point where it's going to negatively affect the lubricant. This is an example where we've done this in another industry, metalworking and machining. But as we start to look at automotive, taking similar approaches and bringing that into automotive. So we're focusing around vibration. Lubricants are at the interface of anything that's moving. And so vibration is a great indicator for what's going on at that interface. But, as we look to the future, new sensors could be designed and integrated to add some additional layers of, maybe the chemical properties. But again, this is still ongoing research for us.
Yeah. You mentioned a very interesting term, IoT, right, for the lubrication space. Like, how do you define IoT in that sense?
Yeah, I mean, I think with lubricants, they can take a few different forms. Like I mentioned with the metalworking example, trying to monitor the actual state of the lubricant, whether it's looking at contamination, looking at some chemical analysis to provide properties. But we've also looked at other cases where even just like automating ordering, right? It's like you have a lot of people don't think necessarily too much about their lubricant stock, right? And they have all the lubricant stored, they're using it, they're pumping it into wherever it needs to go, and all of a sudden they're out and now they have downtime. So even something as simple as providing them a heads up, like, hey, you need to reorder some lubricant, or you need to actually relubricate one of these components. That's a great initial use case. And then as our research progresses and we're able to better understand, map the sensor information into lubricant behavior, then we can start to add layers of complexity to build out that information.
Yeah. The topic of graph neural networks and digital twins, how do you think in the future this will impact kind of the lubricant development?
This is my most interesting project. That's what I'm most excited about. We're kind of moving, and I'm going to take a little side. I'll be brief about AI, and we're starting to see the rise of agentic systems with agentic AI. I can foresee a future where we do something like agentic simulation, where, because we're talking about multiscales, we have different graph neural networks running at the different scales to basically create a near real-time system that is running and providing some of these properties. So you can imagine, and again, still in research, so I'm sorry, it's all theory, but we have the sensor data. That sensor data is passed into, let's call it the molecular graph neural network. So based on the sensor data, that is basically mapped, temperature, pressure, potentially shear environment, any other parameters that we want to incorporate, and then predict, those properties for the CFD scale. But then if we have, there's some research by Google DeepMind and around graph network simulators. So potentially this idea where rather than having to just generate properties, we could stitch the two together, where you have the graph neural network running molecular scale, passing those output predictions to the graph neural network that is running the SPH scale. So when I talk about like agentic simulation, it's kind of like segregating the tasks, but kind of integrating them in one seamless simulation. This is something that I think would be really amazing to achieve, and I think a game changer for the material science industry.
How far do you think we are when it comes to agents? Do you think we're still in the beginning? I think a lot of people say 2025 is the year of the agents. So I'm not sure. What do you personally think about that?
I think we're there. I think, it's people are already using them, and I think they've been using them. I think it's just starting to make its way more into the public eye of what an agent is doing. And there's a lot of back and forth on what an agent is, but just the idea of it going in, like being able to grab data, going in and accessing internal information. I mean, just that alone, I would call agentic, right? And so when I talk about agentic simulation, I'd say, we have our internal material database. So the agents are able to go grab the appropriate materials, go potentially grab the appropriate metadata, like safety data sheets, technical data sheets, or any other contextual information that are enabling the simulation to make the most appropriate predictions, and then pass. And so we basically combining the power of the digital simulation. So essentially enabling that agent to not only fetch data and perform like natural language processing analysis, but also give the agent the ability to go and say, I don't know enough about this. Let me go and run a simulation. There's also that dynamic that I could see happening as well. And that's as simple as setting up an API. And guess what? Dive has an API. So I don't think we're that far away from agentifying simulation in a sense where we can basically give the LLM the ability to say, I don't know enough about this. I want to run a simulation.
Basically, so also doing it autonomously without you explicitly saying, please agent do task X, but it would do it autonomously, which is pretty cool.
Yes.
And then obviously, if you then combine all these agents, you have like agent swarms, which gives me kind of Matrix, vibes.
It's hard to imagine. It really is like the scale at how these things. I think the limiting factor is compute, and so that's where I think GPUs continuously like growing and improving in capability. They're adding more of these nodes every day. That's where we'll see it happen.
Yeah. Do you feel like the job, maybe we're going on a side quest right here. Do you feel like the job description of an engineer or like the responsibilities of an engineer will be kind of quote unquote redundant, which I don't think it will, but it's more like we are going to be augmented as engineers by using agents or AI in general? Is this how you see it as well?
Yes. I mean, again, like the human driving, like the thought process, the innovation I see is still being there for quite a while. But just giving them like, having to go and like just something as simple as deep research, having to go and try to dig through research papers to find new ideas and then try to be able to test those ideas, right? I mean, that process alone for individual projects can take quite a bit for a single engineer. But now give that engineer agent swarms, right? They can multitask. They can go across different projects that maybe are covering different domains, have, these agent swarms be able to access the appropriate information, run analysis, run simulation. And so I just think it's going to give them the ability to do more with less. And in that way, I mean, I think that's pretty standard when we think about AI, but it's going to have more of an impact. So having that core understanding of as an engineer, I think is still going to be very useful for you, because that's only going to give you the ability to guide those swarms much more directly.
Once you guys are there and implement all these agents, then let's have a second podcast and talk about how far we've come.
Yes.
It's going to be a cool podcast for sure. When we talk about leveraging GPU-based simulation, how has it actually impacted your workflow in terms of speed, efficiency, and kind of decision making as well? And what types of GPUs are you using?
Yes, I'm very excited about the GPUs. When we were first starting out running Molecular Dynamics and stuff, we were running on CPU, and like these simulations take a week. Like it's just very time consuming. It's hard to iterate. I'm very much like to iterate fast. So that kind of is like, you got to wait a week to see the results before moving on. With once we move to GPU, we can get it done in an hour, depending on the size of the simulation. So that just in general, like the speed up is significant. When I think about some of my early days with Dive, I started out when they were CPU, and then I got to experience kind of the transition to GPU. And when we were going through using the non-Newtonian fluids, running a grease simulation, definitely, it takes more time, and because of time, it takes more cost, right? So being able to shift from the CPU non-Newtonian simulation to GPU non-Newtonian simulation, now it makes running simulation on greases that much more feasible for us. So now we can actually analyze hundreds of different greases throughout the course of a year, rather than only like 10 or 20 because of limited cost reasons. So it's more cost efficient. we get our results in minutes to hours rather than days. So between all of this, it's been quite an increase in efficiency for us to be able to, like I said, to iterate, try new ideas, test those ideas, get those results, and be able to explore the design space much more than we have in the past.
Yeah. I'm wondering now, maybe as an advice for all the people listening who are also simulation enthusiasts, or maybe using different tools in CFD, what advice would you give them, Rich, when they start a new simulation project? Maybe they want to tap into SPH. What advice would you give them? What are some of the things that you have learned along the way when it comes to simulation? Because you come from the AI space, right? You're not really a CFD engineer in that sense.
Exactly. Yeah, I mean, for me, there's a lot of options out there, right? So like when I was first starting out, I started with OpenFOAM, and then I was like, well, I got some introduction to SPH. I was like, I like SPH, but I want something that's GPU. So there was like so many options. I think it was when I connected with Dive. So I guess the first thing would be, if you are starting out in a new simulation space, definitely reach out to the industry players, because I think they can kind of guide you initially in the right direction. Obviously, they might try to sell you their product, and in some cases that's actually going to be really helpful, because as our experience with Dive, trying to do it all open source versus moving into their ecosystem, it got us up and running much faster. So I think that was something for me that I learned. Like, no, I like experimenting and trying things out, but I also have this idea of like, it's taking me too long to get all of these things situated. So it's definitely like a time versus that ideal knowledge learning curve for you. So having those experts, it's about collaborating. I mean, as you start to look at integrating across these domains, I never expected us to be molecular dynamics experts, SPH experts, mechanics experts. It's just a lot of different domains. So building those connections with these partners, I think it was huge for us to be able to start to actually push progress and start to make some movement in this area.
Yeah. Were you the one primarily driving did you identify kind of the pain inside of the organization and said, well, we can't work with CPUs anymore, like we have to find another solution? Or was it more like a department decision?
I honestly would say it was more of a natural evolution of the industry outside of us, right? In general, computational, we have a strong group internally that is very supportive of this, from some of our management and R&D, but still, it's still young and growing within this company. So I think the effect of going from CPU to GPU really starting to show the speed turnaround, I think will continue to build some momentum in adopting more and more of these practices within our company. So I think it was just, externally the industry started to improve GPUs. And then, yes, because of that, I was like, well, let's get some GPUs. So we were able to get a single GPU in for a little while and just kind of show how that accelerated. But, as we're looking to grow, we are expanding our HPC infrastructure a little bit, where we're taking in 2 H100s, which I'm excited about because, again, having one GPU, I can only run one thing at a time just due to limited VRAM. So having two, I can start to explore, graph neural networks for molecules and graph neural networks for fluids, beyond, being able to test multiple ideas at once. So I definitely think, if I had to say, like, the approach hybrid, like local GPUs, just to be able to test some ideas out, but then cloud infrastructure, like what we're seeing with Dive, it just allows you to do way more once you have that idea locked in and ready to explore.
It's good stuff, Rich. Thank you so much. I learned a lot in this podcast. For sure, if people are interested in reaching out to you, I'm going to post all relevant resources, a link to your LinkedIn profile as well in the description, so people can reach out if they want to. Again, thank you so much. And hopefully there'll be a second part, maybe on agentic AI. Who knows? Oh,
yes. Very soon, we have some interesting work with Microsoft coming up. So I'm hoping that, maybe later this year, I can show you something.
That's great. Awesome. Thanks a lot.
Very good. Have a good one.